Welcome in the second part of the tutorial. So as promised, I will show you the differences or how you can optimize your scripts and some shortcuts. So first of all, you need to understand that this won't work when you have more than one attractor. And even more, it won't work even more if you have different kinds of attractors. So maybe a curve and a point, or a surface and two curves, whatever. But let's add additional curves in the script. So let's reference more than one curve before the curve closest point and see what happens. So now I have free reverse, and well, maybe I will make this a little larger as well. So free reverse, but unfortunately only one seems to work. And the reason for that is lacing works here as well. So I have 2000 right now. I have 2600 points, but I have three curves. So the first point will be, or the distance of the first, the distance will be calculated between the first point and the first curve. Then the distance will be calculated between the second point and the second curve. And then the third point will be compared to the third curve, and then all the other points will be compared to the third curve. So the two first curves will be discarded. So I won't explain how to overcome this using curve closest point, because it somehow exceeds the today's tutorial. I will just give you a hint that you should replace it whenever you are using attractors in your file. You should replace any distance measurement with the pull point component, because pull point is much more general than curve closest point or surface closest point. It just works with any kind of geometry. And it also automatically gives you the distance to the closest geometry. This won't happen here. You would get a distance to every curve, so you would get 3 distances per point. Then you would need to do something with it, and you know, that would be just too much. So let's see what happens if we replace the curve closest point with pull point. Just a reminder, if you want to swap where the wires go, then you need to press Ctrl and Shift shortcut. Ctrl and Shift key combination, sorry, it's not a shortcut. Modifiers, Ctrl plus Shift, and then pick the wires and put them somewhere else. So I will quickly replug those components, and here we are. It works with more than one attractor element. And this will work with as many as you want, and it will also work with different kinds of attractors. I usually never do that, but I will this one. You should never actually combine inputs in that way, so never hold Shift and put this, but I'm doing this just for presentation purposes. Otherwise, don't do it. But I just wanted to show you that you can input points and curves at the same time, and pull point will work. It will sort out what kind of geometric algorithm it needs to use. Okay, so now we have more than one attractor, and now the other thing that I wanted to show you is how to get rid of those components, or actually how to how to find the bounce more quickly. And actually there is a component which is called bounce, and it gives you boundary domain of a list of numbers automatically. So it replaces those 3 components. It gives you the same value. So bounce, feel free to use it whenever you need when working with attractors. And I think that this would be all, actually. Yeah, in terms of this exercise, that would be also, remember that pull point will work with any kind of geometry. This geometry, these are attractors, and that you can use bounce components to calculate the domain of the range of the values that you input. But now let's move to another exercise to practice. Actually, maybe I won't delete that. Yeah, I will save it for you. So another exercise will based, as I mentioned, on a Voronoi diagram. So I will quickly show you how to achieve interesting results using this component. However, you should never overuse it. So I will start with a random population of points. There is a very useful component which is called populate2d. It will give you a very random population of points. And now a quick trick. It has some default values. If you want to change the region, you don't need to model anything or draw anything in Rhino. All you need to do is right-click on region and click on extract parameter. It will give you a component which contains this default rectangle that was in the component. You can of course find it in the params tab as well. The rectangle is here, but extracting parameter is faster. By the way, it also works with other parameters whenever you have default values or internalized values. Anyway, right-click on the region and click Set One Rectangle. Let's increase the size of this region and also make it a square and increase the count of points, maybe 250, and then construct a Voronoi diagram on top of it. Voronoi. By default, it has some large boundary. So these cells exceed far away. In order to counter that, you just need to input the same region for populate2d as for the Voronoi diagram. So boundaries should be set to that same region. And now we have a Voronoi diagram. This is a specific... Okay, every cell represents the area which is the closest to its kernel, to its center. This is how Voronoi diagram works. But this is not for now. So right now I will use attractors to scale those cells a little. So I will use point attractors this time. So I will use points. Maybe 3 of those, why not? And then I will calculate the distance between every center of the cell and those attractors. So you already know that you should use pull point, and these are our points, the kernels of Voronoi cells, and these are my attractors. And I get the distance from each cell to the nearest attractor. And now I would like to scale those Voronoi cells. If they are, let's say that, once again, this will be an inverse proportion. So the closer they are, or actually it's not, it's a normal proportion. So the closer they are, the smaller the distance, the smaller the scaling factor as well. So let's remap those distances. We already know that we can use bounds for the source domain, but let's think of the whole procedure. So the values that we remap are the distances. The source domain are the bounds of those distances, and then the target. We need to construct domain. And let's think of the scale. So I don't want 0 scale because it won't work. So I will input 0.01 as the smallest number. And then I also don't want these cells to grow. So I will use 1 as the largest scale. So once again, in this case, the smallest distances will get the smallest scaling factor, the largest distances will get the largest scaling factor. In comparison with the previous exercise, the smallest distances received the largest radius, and the largest distances received the smallest radius. So you have to consciously determine what is the start and what is the end of the domain. But in our case, let's see what happens. So as I said, I'm calculating a scale factor. And when you are using attractors, you can use them to calculate whatever parameter you want. So you can calculate rotation value, you can calculate scaling factor, you can calculate radius, height, density, whatever. It's just a procedure of mapping one data into another. So in this case, I'm mapping the proximity data, the distances, into, in this particular case, into factors. So I have the cells, and this is the geometry that I will scale. What is the center of scaling? Well, for each cell, the center of scaling is the kernel of the cell. So I will use this population of points as scaling centers. And then the last input is the scaling factor. Let's turn off the preview for the original data. And this is what we receive. So now, as I'm moving the attractor, I am also changing the way the structure looks like, because the cell that is the furthest from any of those attractors will be the largest, and those that are nearby are small. And this might be not entirely what I want, because as you can see, when I'm moving this attractor, I'm also affecting the neighborhood of this one, because the bounds of distances are changing as I am doing that. So when I am moving attractors, I'm also affecting the remap component quite a lot, because I'm changing the source domain. This is a large influence. So we might not want that. This might be something unwanted. So in this case, I would specify the bounds on my own, so the source domain. And this is the way in which you can adjust a range of influence. Range of influence of an attractor. So let's construct a domain. Maybe I will show you an alternative way of quickly creating domains. You can simply write something like, I would write maybe 15, 0 to 15 in a panel. So this is a text, but Grasshopper will understand that this is a domain. If you use two numbers separated by a word to, then it will understand it as a domain. So if you want to quickly test something, then this will work. Unfortunately for us, if I use this parameter, something wrong, something strange happened. And what happened is actually some of the distances were larger than 15. And you remember what happens when a number is larger than the source domain. If it's larger, like this 7.5 was, then the resulting value will be also larger than the target domain. In our case, the target domain is set from 0.01 to 1, but if a distance exceeds this 15, then the scaling factor will also exceed 1. This is why sometimes those cells are growing larger than they were at the beginning. And we certainly don't want that. And this is where or when you should use the other output from the remap numbers component, which is called clipped. Clipped means that the result will always be clipped to the bounds of the target domain. So even if it is larger, or if it exceeds the source domain, it will be clipped to the largest possible value. So in this case, 7.5 would not be remapped to, or it would be mapped to 35, but after clipping, it would be brought back to 20. If I use clipped instead of mapped, then the cells that are further than 15 will just stay intact. The scaling factor will be set to 1. And now you can see that you can clearly see the range of influence of these attractors, and I would call this exercise as done.